Welcome back, everyone. Today we'll be taking a closer look at permutations, which will tie into how it's possible to solve the Rubik's Cube blindfolded. An important thing to notice about permutations is that they break up into what are called disjoint cycles. And disjoint just means they're separate. So, with this example of sigma from before, we could track where things go. So 1 goes to 4, which then goes to 3, which then goes to 5, which goes back to 1. And we see that 2 is left alone. So there's these 4 cycle, and then 2 just stays where it is. So this one breaks up into a 4 cycle and a 1 cycle. And then tau here, if we track it, we'll see that it goes through all of the numbers before it goes back to 1. So that's a 5 cycle here. And for another example, I'll write another permutation down here. So here, if we track it, 1 goes to 2, which goes to 3, which goes back to 1. So that's a 3 cycle. And then here, 5 and 4 swap with each other, so that's a 2 cycle. So this has a 3 cycle and a 2 cycle in it. Now, we can do this to the cube as well. So if we just turn the right face once clockwise, we can track where the pieces came from. So if we start with this piece, which came from here, so that goes to here, which goes to here, which goes to here, and then back. So that's a 4 cycle of the corners. And then the same with the edges, it's another 4 cycle. And then if we do an R2, if we track it now, we'll see that this swaps with this, so that's a 2 cycle. Then here's a 2 cycle here, and then these 2 swap, and these 2 swap, so it's just 4 2 cycles. So now we'll introduce some notation which will be a little more convenient than writing out this whole thing. Instead of writing out the whole permutation, it can be more convenient to just write what the cycles are. So we have a notation for that. So this one here, we would write 1, 2, 3 for the 3 cycle. And what this means is that it carries the first number into the second number, into the third number, and then once we reach the end, that means we go back to the first number. And then we would multiply this with the second cycle, which is 4, 5. And we can actually write this multiple ways. For example, we could write it 5, 4 instead of 4, 5 because it's the same. But we could also write this first cycle as, if we want to start with 2, 2 would go to 3, which would go to 1, which would go back to 2. And also, instead of writing this cycle first, we could write this cycle first. It doesn't really matter what order we write the cycles, as long as we have the correct ones. The nice thing about the cycle notation is that it makes it easier to invert the permutation. All we actually have to do is invert each cycle independently. And the inverse of a cycle is just writing them in the backwards order. So the inverse of this, for example, would be 3, 2, 1, and then 4, 5, or 5, 4, it's the same. And of course you could write this with 1 going first, which would be this. Another nice thing about looking at the cycles is it can tell us what the order of an element is just by looking at the cycles. So let's consider the permutation that we get when we do R2, U2. So now let's look at the cycles here. So this piece came from here, and this piece came from here. Then this one goes back here, so that's a 3 cycle there. And then we have another 3 cycle here. So that's 2 3 cycles for the corners. Then with the edges, we have a 2 cycle here and a 3 cycle here. Now the order of the permutation is going to be the least common multiple of these cycles. So the order of an n cycle is just n, because you repeat it n times and it goes back. So in this case, since we have only 3 cycles and 2 cycles, the least common multiple is going to be 6. So let's see. We'll just try doing this 6 more times, and it should go back to solved. So we've done it once, now twice, 3 times, 4, 5, and 6. And you can do this with any other permutation that you want. So, for example, we could do just RU. And here it actually gets a bit tricky. We'll get to why in a second, but here, this corner came from here. So we have a 5 cycle of corners. But then this corner here, this actually is in the right place, but it's twisted. So if we have a twist of corners, that's going to actually contribute 3 because you have to twist a corner 3 times before it goes back. So that's the complication that arises because we have to consider both the orientation and the permutation. So we have a 5 cycle and essentially a 3 cycle here. Then with the edges, we have a 7 cycle. So if we multiply those 3 numbers together, I should have done this before I started speaking. Give me a second. Then we get 105. So if we repeat RU 105 times, it'll eventually go back to solved. But I don't really want to repeat it 105 times for you here, but you can try it on your own. And similarly, we saw the corner twist before. If we have something that flips an edge, then that's essentially a 2 cycle. So those are the 2 tricky things to look out for. Now the next important observation about permutations is that all of them can be solved just by swapping 2 numbers at a time. So I'll demonstrate. I'll mix these 5 numbers up. So now I'm going to solve it by swapping just 2 at a time. So I'll start here. I want to get this 2 in the correct position, which is here. So I'll just swap these 2. And now I want to put this 5 in the correct position, which is over here. So I'll swap these 2. And now just these 2 need to be swapped. And you'll notice that essentially what we did was we did a 3 cycle here and then the 2 cycle. So breaking it into the cycle decomposition first, you can then break those cycles into 2 cycles. So if you have just a 2 cycle, then you can solve it by just doing 1 2 cycle. And if you have a 3 cycle, it's going to take at least 2 2 cycles. You could do it some other way that would take more, but the minimum is 2. So, like here, you would do 1 and then 2. And it turns out if you have an n cycle, so if you have n numbers cycling, it's going to require n minus 1 2 cycles to solve. And as it turns out, if the permutation you have, if you can solve it with an even number of 2 cycles, then any other way that you can solve it, it's going to require also an even number. So for example, if we had this 3 cycle from before, we could swap these 2 first, and then we could swap these 2, and then we could swap those. So that's 3. So this is solved now, but now we have to solve this. So that gives us 4. So it's still an even number of swaps that we had to make. And this evenness versus oddness is called the parity of a permutation. So if the parity of your permutation is even, that means that it requires an even number of swaps to solve. And if it's odd, it requires an odd number of swaps to solve. And odd cycles, so a cycle of an odd number of things, correspond to even permutations. So a 5 cycle would require 4 swaps, which is even. But if we had something complicated, like if we have a 3 cycle and a 2 cycle, this is even here, but then this requires odd, so in total it's going to be even plus odd, which is going to be odd. So it gets tricky when you mix multiple permutations together, but you just add up the parodies of each corresponding cycle, and then at the end you can tell whether it's even or odd. So let's apply this to the cube. Let's just look at the R from before. So we had a 4 cycle of corners and a 4 cycle of edges. So a 4 cycle is going to require 3 swaps. So that's an odd permutation of the corners, and then again an odd permutation of the edges. So in total, this whole permutation that we've done is even overall. And since every move on the cube is some sort of single move like that, that tells us that we're never going to have an odd permutation in the cube. So we can't just have a 4 cycle by itself. We have to have a 4 cycle of something else at the same time. And we also couldn't have just a 2 cycle. So we couldn't have something like this. We have to have something else swapped somewhere else. Now some of you might have looked at solving big cubes already, and you might have heard the term parity. We can do a similar thing to what we did on the 3x3 to see where the parity comes from. So if we do just an outer block turn like this, you'll see we have a 4 cycle of corners, and then a 4 cycle of edges, and then another 4 cycle of edges. So that's 3 4 cycles so far. But then on the centers we have another 4 cycle, so that's 4 4 cycles, which is even. So where does the parity come from? Well, it actually comes from a slice turn like this. So here, if we track it, we'll have a 4 cycle of edges, and then we'll have a 4 cycle of centers, but then we'll have another 4 cycle of centers, so that's 3 4 cycles, and that's where the parity comes in. It's from these slice moves like that. So the way that a blind solve works is you look at the different cycles, so you memorize the cycles, but actually you can just memorize swapping 2 pieces at a time. Except we just said that we can't swap 2 pieces at a time. So what they do is they solve corners and edges separately. And when you're solving the corners, you swap 2 corners at a time, but then also you swap 2 edges. So if we had a 3 cycle of corners like this, what you could do is you swap these 2 first, and at the same time you're swapping these 2 edges. So now these 2 edges are swapped, but now you're going to swap these 2 corners and then swap these edges back. And you can do a similar thing when you're solving the edges. And it gets a little bit tricky if you have an odd permutation of the corners and the edges, but there's ways to deal with that. Now you might be thinking, that seems really difficult because now you have to memorize tons of different algorithms to swap every possible 2 corners and 2 edges. But as it turns out, you can actually just use one algorithm to swap the corners and one algorithm to swap the edges, and you can apply that by doing setup moves. This is called conjugation, and we'll talk about that next time.